At 2:18 a.m. on October 7th, 1942, the night shift horn blew at Plant 9 on the south edge of Cleveland. Ohio, and no ceremony, no speeches, just a click of time cards, the slam of steel doors, and the steady roar of furnaces waking up like a living animal. Outside, Lake Erie wind pushed rain against the windows and sheets. Inside, the air was hot enough to taste. Cutting oil hung in the light, like a thin fog. A line of crankshafts, each one longer than a man's arm, sat on pallets, cold and unfinished, waiting to become the rotating spine of engines that would power trucks, tanks, landing craft, and bombers. The foreman didn't give a motivational speech. He didn't have to. He only said, "We're behind by 24 engines." And then the machine started moving again. They didn't know it then, but the next 12 hours would decide whether entire convoys moved or stalled on roads and beaches thousands of miles away. Engines are not weapons in the romantic sense. They don't have flags painted on them. They don't make dramatic speeches. They don't show up in victory photographs. But in industrial war, the engine is the backbone. No engine means no truck. No truck means no fuel. No fuel means no armor movement. No artillery resupply. No evacuations, no retreat, no pursuit. No war at all. Just men stranded with empty hands. And the enemy understood that. They targeted refineries, rail yards, machine tool plants, and shipping lanes because they knew a simple truth. You can replace rifles faster than you can replace horsepower. A tank without an engine is a bunker. A bomber without an engine is scrap. A landing craft without an engine is a coffin. The math was brutal that a single front had consumed thousands of engines in a year, destroyed in combat, burned out by dust, drowned by salt water, shattered by shrapnel. Every missing engine was a missing mile of movement, and movement is what wins, so the war became a production race. Not just who could build the best machines, but who could build enough engines, fast enough, consistently enough, and correctly enough to keep armies alive. That's why, in 1941 and 1942, a quiet directive moved through boardrooms and government offices like a classified order. It wasn't called a battle plan. It was called a production program. It demanded one thing: mass engine production at a scale that peacetime industry had never attempted. And it chose places like Cleveland because Cleveland already had the sound the program needed. The sound of heavy steel being turned into precision. But there was a problem. You can't simply decide to build engines faster. An engine is not a chair. It's not a rifle. It's a controlled explosion repeated thousands of times per minute. That means tolerances. That means metallurgy. That means inspection. That means systems that don't bend just because the calendar demands it. Plant 9 was chosen for reasons that had nothing to do with patriotism posters. IT sat on rail lines that could pull in alloy steel from Pennsylvania and ship finished engines to ports on the Atlantic without touching congested East Coast cities. It had water access through the Great Lakes, cheap bulk transport for castings and raw stock. It was surrounded by smaller tool and die shops that could be absorbed like tributaries feeding a river. And it had people, machinists from the auto industry, laid off during the Depression, men and women who already understood that if you misread a micrometer by a hair, the entire assembly becomes junk. Here's what most people don't know. The secret of mass engine production wasn't a single factory. It was an ecosystem. Foundries pouring blocks, heat treat plants hardening gears, gauge labs calibrating measuring tools, rail dispatchers scheduling shipments like surgical operations. The engine program didn't just build engines. It built a supply chain that could survive sabotage, shortages, and human fatigue. And fatigue mattered, because by 1942 the plant ran 3 shifts, 24 hours a day. The work didn't pause. Only the people did, briefly. Before returning out on the second shift, Lillian Porter worked crankshaft inspection. She wasn't an engineer. Before the war, she worked at a dress shop downtown, measuring hems and stitching seams. Now she measured journals and fillets, running her fingers across polished steel like it was fabric, looking for the tiny imperfections that could become catastrophic later. She kept a photograph in her locker of her brother, James, wearing an army uniform, smiling like he didn't understand what was coming. His letters arrived late, stamped and censored, full of empty phrases because he couldn't say where he was. She couldn't tell him what she did either. But she could look at that photo before each shift and remember the rule that mattered more than production quotas. If you let a bad crankshaft through, someone you love might die in a place you can't pronounce. Quality control wasn't a department. It was a religion. The crankshaft started as raw alloy steel, thick, heavy, brutal. It was forged under press hammers that shook the building. Forging aligned the metal's grain like with fibers, giving it strength where it mattered. But forging was only the beginning. After forging, the crankshaft went to heat treatment. It was heated until it glowed a dull orange, then quenched to lock in hardness, then tempered so it wouldn't become brittle. Too hard and it cracks. Too soft and it wears. That balance, hard enough to survive, tough enough not to shatter, was a quiet miracle every engine depended on. Then machining began. First, rough turning on massive lathes to bring the shaft into approximate dimensions. Then grinding, where the final surface finish and diameter were achieved. The grinding wheels screamed against steel with a sound that got into your teeth. Coolant flowed constantly, milky and sharp-smelling, carrying away heat and metal dust. If coolant flow dropped for even a minute, the journal could heat, expand, and warp. A warped crankshaft doesn't fail immediately. IT fails later. IT fails when a truck is climbing a mountain with wounded men in the back. The tolerance on a main journal was often held within 0.002 of an inch. That's thinner than the thickness of a human hair. And the plant didn't check it once. They checked it again. And again. Gauges were calibrated daily. Micrometers were kept clean like surgical instruments. In the gauge room, the air felt colder, quieter, as if the building itself understood the seriousness of measurement. The math was brutal. It was also simple that a V-type engine might require a crankshaft, a camshaft, dozens of bearings, pistons, rods, valves, springs, gaskets, gears, pumps, and fasteners, hundreds of parts that all had to fit together as if they'd been born as one. If any one part was out of spec, the engine might still run in a test cell. It might even pass for an hour, but then it would seize, or throw a rod, or burn a bearing. And when an engine fails, it doesn't politely stop. It destroys itself. Shrapnel inside a block, oil fire, locked drivetrain, a vehicle turned into an immobile target. That's when everything changed, because by mid-1942, production targets were no longer ambitious. They were non-negotiable. The program demanded a certain number of engines per day, and the plant responded by breaking time into smaller and smaller units until the day felt like a single continuous operation. One line produced crankshafts. Another line produced cylinder heads. Another produced pistons. Subassemblies moved on carts that squeaked under load. Engines moved down the final line like bodies moving through a hospital. Stations for installing bearings, then crankshafts, then rods and pistons, then timing components, then heads, then accessories, starter, generator, fuel pump, water pump. Each station had a stopwatch rhythm.an engine every 14 minutes. That was a target, which meant more than 4 engines per hour per line, across multiple lines, around the clock, hundreds per day, thousands per month. And every one of them had to be able to run at operating temperature, without oil pressure collapse, without coolant leaks, without vibration that would shake it apart. But there was a problem. Engines were coming back in the field with random failures. Not a design flaw on paper. Not a single part that was obviously broken. The reports were vague. Low oil pressure at sustained load, bearing were accelerated, occasional seizure after long operation. The kind of problem that makes commanders furious because it doesn't give you a clear enemy to blame. The plant managers wanted to blame the field mechanics. The field mechanics wanted to blame the factory. The engineers wanted to blame the war. Except one person noticed something. Arthur Art Delgado worked in the test cell building, where engines were bolted down to stands and run under load before shipment. Test cells were loud, violent places. The exhaust heat shimmered the air. The engines screamed against dynamometers that resisted them like invisible walls. Men wore ear protection that barely helped. Art kept a notebook in his back pocket, pages stained with oil fingerprints, filled with engine serial numbers and handwritten observations, oil pressure curves, temperature spikes, vibration notes. It wasn't required. It wasn't praised. It was just something he did because he didn't trust random. One night, he started comparing the failures to shift logs. Engines assembled on the late shift were failing more often than engines assembled on the day shift. Not dramatically, but enough to matter. And then he went deeper. He looked at a single subcomponent. The oil pump relief valve assembly, A small plunger and spring that controlled pressure by bleeding excess oil back into the sump. IT was cheap. IT was simple. IT was overlooked. And the parts bins. The relief valve plungers arrived coated in a thin protective oil from the supplier. That oil wasn't the same as the engine oil used in assembly. In summer humidity, mixed oils could create a film that trapped microscopic grit. So small it looked like nothing. When the relief valve moved under pressure, that grit scored the plunger surface. A scored plunger could stick. A sticking plunger could drop oil pressure under sustained load. Not always, just sometimes. Just enough to kill an engine at the worst time. Art took his notebook to his supervisor. The supervisor told him to stop imagining things and focus on output. Art went to the test engineering office. He was told to submit a form. He wrote a memo anyway, attaching serial number lists, failure rates, shift correlations, and one recommendation that sounded insulting to management because it implied they weren't already perfect. Standardize the cleaning and pre-lube procedure for the relief valve plunger and spring. One solvent, one method, one inspection step, every shift. No exceptions. For 2 weeks, nothing happened. Then an engine seized in a test cell. The failure nearly injured mechanic. The investigation landed on someone's desk with urgency, and suddenly Art's notebook didn't look like paranoid. IT looked like a warning the directive went out. Solvent wash and air dry for every relief valve plunger, magnified visual inspection for scoring, and a controlled prelude with the same oil used in final fill. The change added less than 2 minutes to assembly. Management hated that. The war loved it. Within 6 weeks, the random low oil pressure failures dropped by more than half in test cells. Field returns declined in the next quarter. The problem didn't vanish. War never gives you perfection. But it stopped being mysterious, and that mattered. Mystery kills planning. Planning is war. Now the engines moved where they were needed. They went into trucks that carried fuel to airfields, into tractors that pulled artillery through mud, into landing craft that shoved through surf with men crouched low and silent inside, into generators that powered radar stations on windswept cliffs, into tanks that needed torque more than elegance. In an operational world, engines don't get applause, they get punished. Imagine a convoy route in North Africa. Sun bleaching paint. Sand finds its way into every seal. Temperature swings at warp metal. Drivers run engines hot because they have to. They can't stop. Stopping means becoming a target. Oil changes are delayed. Filters clog. Bearings wear. The engine is asked to do what it was never asked to do in a civilian life. Run hard, run long, run dirty, run wounded. But because factories learned how to hold tolerances and repeat them at speed, those engines kept running long enough for logistics to function. And logistics was a hidden battle. The unit that receives fuel on time can maneuver. A unit that receives ammunition on time can hold. A unit that receives replacement parts can recover. A unit that loses engines loses movement, and movement is choice. Without choice, the battlefield dictates your fate. The math was brutal. .1 stall fuel truck can delay dozens behind it. One broken down prime mover can leave artillery stuck in soft ground. One failed engine in a landing craft can cause a boat to drift sideways into surf, where it becomes a collision point, where men drown and equipment sinks, and the whole landing timetable slips by minutes that become casualties. Engines didn't win a war by being heroic. They won by being present, BY being enough, the BY being reliable just often enough to let plans survive contact with reality. Lillian Porter learned this when she saw a bulletin board notice, an internal plant memo, not meant for newspapers, describing an overseas report. A convoy had reached its destination after a sandstorm because vehicles maintained operational integrity under sustained load. That phrase was cold and bureaucratic, but she read it like a letter. It meant engines didn't quit. It meant movement continued. It meant someone's brother might still be alive. And Art Delgado kept writing in his notebook, even after the directive, because the war kept generating new problems. Coolant contamination, improper gasket seating, a batch of bearings that wore too fast because heat treatment drifted. The factory became a living organism of feedback. Field report engineering to process change to inspection, inspection to output. That loop, fast, disciplined, unromantic, was a real innovation. The aftermath never looks like the posters. When production peaked, the plant was loud day and night, its windows glowing in winter darkness, its parking lots full, its break rooms filled with people eating in silence because there was no energy left for conversation. Then the war ended, and the urgency evaporated almost overnight. Orders were cut, shifts were reduced, the test cells went quiet. Some lines were repurposed for civilian engines, others were dismantled. A few buildings became warehouses. Years later, new tenants moved in, then moved out. Some structures were demolished. The ground where crankshafts once sat on pallets became anonymous pavement, and old museum, an old statue, an old plaque that says, "Here, thousands of ordinary people learned to turn raw steel into controlled explosions that kept armies moving." That's the legacy of mass engine production. It is everywhere and nowhere at the same time, embedded in the fact that modern industrial systems still use the lessons learned when failure had a body count. Because in the end, engines are not just metal, they are trust. Trust that a machine will respond when a driver presses a pedal in the dark. Trust that oil pressure will hold when the load increases. Trust that heat won't turn into fire. Trust that the invisible work of a factory worker, someone you will never meet, will keep you alive if you're discovering stories from history that most people never hear. Consider subscribing. We tell the stories behind the machines, the systems, and the workers who built victory without recognition. That if you made it this far, thank you. We know these are long. We know the algorithm prefers faster, simpler, shorter, but history isn't short. And the work that kept wars moving wasn't simple. For the comments, what do you think matters more in an industrial war? Brilliant strategy or the quiet, disciplined production that makes strategy possible?